Okay, please have a look at this example. So we count the number of words a child reaching school age should know. So there's a claim. A child should know more than 2,000 words already. Assume that the number of words follow a normal distribution. Now it has to be assumption because the number of words, it's countable, right? It would be a discrete random variable if you say X is the number of words. Being a discrete random variable, how can it follow a normal distribution, right? Normal distribution is continuous. That's why it's just assumption that we approximate that distribution of the number of words is just approximately normal. So if you connect the dots of the probability match function, you see there's approximately a line. So we are using that normal line. Hypothesis setup, mu, right? Mu is, in general, a child reaching school age should know, right? The number of words a child should know in general. They should know this or more. 5 kids give you the random sample. These 5 kids know, on average, these many words. And the standard deviation of these 5 kids, 100. So this sentence, their mean and the standard deviation, that means this mean is the sample mean. This standard deviation is the sample standard deviation. So when you write information about these numbers, you need to write in a way X bar observed. Okay, don't write, oh, mean is mu. Mu is this, sigma is that. No, both wrong. X bar is this, S is 100. They use this as the significance level. So in your tests, whatever quiz or test or hypothesis testing, the setup is exactly this. So all you need to do, you just need to read carefully, especially where you see the words standard deviation. You have to judge whether you use it in terms of sigma or S. Whenever the standard deviation is calculated from your random sample, okay, just keep in your mind what's the difference between a random sample and population. 5 kids give you a random sample. And what's the population? Population would be all the children reaching school age in the whole world, right? Their standard deviation would be the sigma, not this, right? These are from the 5 kids. So once you are able to write this all out, the question is very clear and simple. You just can't misunderstand, right? Use critical region, conclude the test, and then use the p-value to conclude the test. So you just need to know all the methods. Unfortunately, there are always students saying the wrong thing, right? Here, critical region, but some students would read it as confidence interval. Don't imagine things, right? Just highlight in your test critical region. Then you use critical region. I'll write everything out based on that paragraph. Since the two questions are very similar, I'll write all steps for the first one. The second one, I'll leave the steps to you. Okay, hypothesis testing. Okay, one sample. Hypothesis testing for mu. Okay, no space. Since the final exam is so soon, so right now, you can already consider it, for example, today's lecture, as a review for your final, because you've learned all the 3 methods. And now it's just a reminder, okay? If you think, oh, this is new, I've never heard of it, then there's something wrong. You forgot already too much. So just keep every sentence, whatever I said today, in your mind when you review When you read the questions on hypothesis testing, you ask yourself the same questions. Now, X is the number of words a child reaching school age knows. Right, right. The number of words a random child should know or knows. We assume that this X is normal. I introduce mu and sigma squared. There's a tool. Okay. Population mean, population variance. This is the population standard deviation. But they are both from the population because this is the distribution, right? You can't. Okay, something else I've seen, you don't copy this. I've seen students writing normal distribution with X bar and S squared. No, okay, just this is just so ugly. You can't write the sample statistics into the distribution. The distribution is always from the population, right? This is forbidden. Now the test is on how many words a child should know on average. The pair of hypotheses are always given to you for this course. We don't ask you to choose where to write which significance level, point one. A random sample of 5 kids. And sample size. How many do they know on average? This is my X bar observed, right? Observed from the sample. They know this many, and their standard deviation is 100. Now let's start the first method, critical region. What's the definition of critical region? Critical region is a region that if your sample is so bad in supporting H0, what do? You reject H0, right? As simple as that. So critical region gives you a judgment whether your sample supports H0 or not. What kind of sample would be bad in supporting H0? In other words, what kind of sample would be bad? No, would be bad in supporting H0. It would be good in supporting H1. Now, if these 5 kids are all so smart, right? They know so many words. For example, they know on average 5,000, right? 5,000 words is a lot. Now, if they know, so their X bar observed is 5,000, you would think that all the children, right, in the world should know more than 2,000 because you trust the sample. You don't trust either or of these, right? They are just hypotheses. They are guesses, right? You have no basis in believing any claims, but you believe the random sample. So if 5 children know on average 5,000, you would accept this and reject that. That means if your sample mean is too big, right? So it's so big, bigger than what? We need to find this value, whether this value is 5,000, that's extreme or not. We need to find this. To start this method, make sure you know that it is X bar, right? Not mu. And make sure you know the larger, the less supportive to H0, the more supportive to H1. So these 2 things would be a good start. Now, this is just a symbol. You can use X star or ABC, whatever. It's an unknown constant that we are going to find now. How to find the critical region? We start with alpha. Alpha, the significance level, is defined in hypothesis testing as the probability to make type 1 error. Make sure you write all the steps, okay? Don't cut corners. What's the definition of type 1 error? It is you reject H naught when it's true. Then what would make you to reject H naught? For this method, critical region, a bad sample would make you to reject H naught. What kind of sample is bad? As I've argued in here, if the sample mean, okay, sample mean is too big, is bigger than a certain number, then I would accept H1, reject H naught. When it is true, when H naught is true, I just copy. What happens when H naught is true? The mu is 2000. Look at this probability. The probability that the sample mean is is too big when mu is that. We have three things in here. X bar is the sample mean. Now don't use this. This is the observed sample mean. You leave this away from this probability. This sample mean X bar, capital X bar, is whatever sample you get. That average, so your any sample's average, this is a variable, right? This is a variable. The variable is greater than a unknown constant. So this is a number that we are going to find. When mu, what is mu? Population mean. When the population mean is 2000. We need to use this variable and find the probability that this variable is whatever, whatever. So let's look at this variable. X bar is coming from X, right? X follows this normal distribution. What is X bar? X bar is the average of a list of X. So X is a random child. The number of words a random child knows. We have the first child knows this many, the second one knows this, and you average them out. This is a linear function of normal variables, so it's normal. Handout 4, linear function of random variables, taught you all these. However, if you standardize X bar to Z, you'll find out that sigma is not given, right? Sigma is not there. When sigma is not there, you don't standardize to Z. You use T. When you use T, here is S. I explained this when we get here, and we have to show it now. In fact, when you have hypothesis testing on mu, only two options, either Z or T. When you write all these up, so this is a setup for your hypothesis testing, you should immediately decide whether you use T or Z, right? You need to work on this in the very beginning. So no matter which method the question asks you to do, you just keep using whatever you decide in the very beginning. Otherwise, if you have already muscle memory, oh, X bar, now I standardize to Z, then you are going the wrong way. Now, X bar, the variable, I show this, so X bar, the left-hand side is changed to a T. You do exact same for the right-hand side. This X bar, this would be a number, a treat. In the same way, don't forget the condition when mu is 2000. Why do I use all this? Because I need to show the t. This t statistic has a parameter, degrees of freedom. So if you want to remind yourself, you just write a minus 1. Okay, it's not, am I allowed? No, this is just for your own safety. You just write a minus 1. This side, x bar, we don't know yet. But we know the condition, mu is 2000. This is the moment to substitute. Right? I'm using the given condition, and I'm using the sample information, sample standard deviation, 100, and it's 5. So I can also write here as 4. I don't need to calculate any later, so I show it there. Now we have a probability that the t statistic is greater than something, right? In this something, there's only one unknown. This probability comes from alpha. Alpha is given. Whenever I see the probability has a z or t clearly shown, I will draw it. This is the distribution for t, right? All the t values at the bottom, and this is my t distribution with degrees of freedom of 4, and it's symmetrical about 0. The probability that t is greater than something is this small. The probability that it's greater than something to be small, it has to be positive. So this positive value refers to all these expressions. You need to look at the t table. Now I don't have it here, but I know this value. So make sure you know where to look on the t table. This is the t value that you refer back for all these. And find this unknown. This star value. Now the question asks you to find the critical region. And then you just write a sentence to claim that I found it. Okay, the critical region is this. If you just give a value, what does it mean? Does it mean x bar has to be equal to this or less or greater? Which side? You have to pick the right side. Critical region is if the sample mean is more than this. Let's have a quick reminder of this method. Okay, we found the critical region. Let's just pause for 5 seconds here and see whether it makes sense. X bar, the sample mean. If the 5 kids, right, we have the 5 kids there, if they know on average more than this number of words, this value is greater than 2000. If they know even more than this value, then we would think that all kids would know more than 2000 instead of equal, right? So instead of exactly 2000 or less than 2000. So this, the combination of greater and a value here greater than 2000 makes sense to be a critical region. So this is just part of the question. I show you the question in case you don't believe me. Find the critical region and conclude the test. Right, 2 parts. Right now, we did the first part, find the critical region, and then we need to do the conclusion. We use the critical region. Look at our sample. Our sample, the 5 kids there, know on average 2,200. This value is greater than this critical value, meaning the sample mean falls in the critical region, so we reject H naught. This is the complete word for a critical region method. Next question. Find the p-value and use it to conclude the test. Still 2 parts. Now, what's the definition of critical? No, p-value. P-value is a probability. It's a probability to have a worse sample than the sample you have is supporting H naught when H naught is true. Okay, this is a long definition. Let's look at this test. Now we'll have to refer back to this test again and again because we need to understand what we are doing. P-value is a probability to have a worse sample than the sample we have is supporting H naught. What sample would be bad in supporting H naught? Now, we've made all the arguments before. If the sample mean is too big, right? If the sample mean is even bigger than the current one, then it supports H naught even less. So that's the correct direction to go. The probability to have, so this X bar is any 5 kids, right? Not the 5 kids you have right now, just any 5 kids to have a worse, no, it's not worse kids, even smarter kids than the 5 you've got. That in the sense that the number of words they know is even more than the 5 kids we have. Because the more words they know, the less supportive for H naught. It means they know a lot more than 2,000 words. So we would support H1. Don't forget when H naught is true. So when I describe this p-value definition in words, it sounds so long, right? Never ending. But in here, p-value is a probability to have worse sample than the one you have in supporting H naught when H naught is true. The fact is quite short. But in this definition, again, don't write anything else. If you write X wrong, write mu even worse. So X bar, the sample mean, the direction, and in here, even worse than the current sample mean. It's always the first step that's the most important because from now, you know what to do. Right? We did the exact same in part A. You change this X bar to T. Since we've decided to use T for this question, keep using the same T. Okay, don't change your mind. Oh, I want to show I know Z, so I use Z. No, don't show off. For this step, I only did this transformation in order to show T in the next step. When H naught is true, mu is 2000. Now I see the T. On the other side, X bar observed is given. Mu is in the condition. S is given, and we know 5, and 5 minus 1 gives you the degrees of freedom. Calculate. That is 4.47. I showed you how to do this trick, but I don't know if you still remember. We have to do a little trick here because this 4.47 is most likely not available on the T table. Okay, I have to find the T table somewhere. Here we are looking at 4.47 in the row of 4. Degrees of freedom is 4. 4.47, 4.7, not there. But 4.47 has two neighbors. 4.6 here, 3.7 there. So you find the closest neighbors. We don't use, oh, now I do alpha 0.1, then I just look at here. No, you give the best estimate, the closest estimate to your question. Where I'm going to copy these two t-values in the row of 4, of course, and their corresponding right tail probabilities. Right tail. To the left of our 4.47, we saw this 3.7 with a right tail probability, this. Okay, this curve is the t-distribution with 4 degrees of freedom. What we need for our question is the 4.47. Okay, 4.47. We also need the right tail greater. Okay, this is our p-value. The other side neighbor, 4.6. Since the trend, of course, this line in the middle is 0, so we are looking at the 3 positive t-values. Since the trend is declining, so it's a decreasing line, as the t-values going up, right, from 3.7, 4. As they go up, the right tail, the shaded area of the right tail, would go down. That's why the p-value must be less than this and greater than that. I make some arguments here. You can choose to draw like this, or you can write sentences, or you do both. So this 4.47 because this value is between these two, so the probability, this p-value, is between these two. Right? This is the first part of our question. Find the p-value. Okay, we have the estimate of p-value. Is this estimate workable to conclude? Yes. We only need to compare p-value with alpha. Because this p-value is less than alpha, which is 0.1. So no matter what the p-value actually is, for as long as it's between these two, it's less than 0.1. Since p-value is less than alpha, reject H naught. Why? a small p-value would make us to reject H naught. It still comes back to our definition of p-value, right? Because p-value is so small, it's extremely small. That means it is very difficult to find a sample even worse than this one in supporting H naught. Because it's so difficult to find a worse one, it means the current sample is already bad enough in supporting H naught. If the sample is so bad in supporting H naught, we don't support H naught, right? That's the conclusion. So we reject H naught. So you see the importance of understanding the definitions, right? It's everything comes from the definition. So this is our first example of today. As I said, I'll do the second example a little bit faster. I'll write less, but I'll go to the critical moment because the second example has a different side. Instead of the first one, mu is this or more, the second example is mu is less. So the opposite side of the test. So this is the example. Cereal. We have packages of cereals. It's printed on the package that each pack should contain at least 20. Okay, this is the weight of the cereal. The company claims that every pack should have at least this much. Suppose that the weight follows a normal distribution. It shows clearly that our variable x is the weight of a package. A customer buys 4 packs and he wants to test whether the claim is true. These 4 packs has the mean weight and the standard deviation of this and that. Please agree with me that this is very clear, that this is the mean of the 4 packs and this is the standard deviation of the 4 packs, right? These are not whatever the company claims, right? This is from the random sample. Look at the customer claim, and the company is keeping a promise. We do it at alpha at this value. Again, p-value, critical region method. Okay, let's set up the test. X is the weight. The answer is okay, let's skip all that. Weight of a random package. Assume X to be normal. Is sigma given? No. Don't worry about why it's less. In the exam, you will be given these tools, so don't worry too much. Now, I chose H0 to be equal, H1 to be less because the sentence we saw, that this is the claim. Each pack should weigh at least 20. At least 20. That means, okay, the claim, the company claims the average weight, right? It doesn't claim each one should be at least. That would be very risky to claim. So mu is at least, right? This is the sign for at least. This is the claim. Whenever we see this equal, it goes to H0. So this whole thing goes to H0. The complement of this goes to H1, right? Now you see the perfect match. Okay, we are doing this test, a random sample. 4 is the sample size. The average weight of the 4, standard deviation of the 4 is this. Right? This is already a complete setup, right? As neat as this. From here, as I said, it would be a good moment to decide whether you use Z or T. You don't know sigma. Obviously, you need a T. Decide right now. P-value. The probability to have worse sample than the one you got in supporting H naught when H naught is true. What sample would be worse in supporting H naught? The smaller or the lighter the pack, the less supportive to H naught, because the lighter the average weight of 4, the more you support H1, right? Mu says it's less than 20. So if I have the average of 4 packs give me only 10, right, I would say it's definitely less than 20. So the population mean can't be greater or equal to 20. So this probability, the lighter, the less you support H naught. When H naught is true. So this is the most important step. Right symbol, right direction, and you are comparing with the current sample mean. That's why it's a good idea to write observe. Otherwise, if you don't have this, it's all the same. It's confusing. So I skip some steps. Okay, just maybe one step that I saved. We'll come to this one. Calculate everything out. We'll have a value. This, right? This is quite strange because it's -4. Maybe 4 is not on the table. Negative is never on the T table. So what to do? You need to realize that T distribution is symmetrical about 0, no matter what the degrees of freedom is. But we are looking at T, okay, all T values are at the bottom. T less than -4. -4 is here, less is to the left of it. So this is our p-value. Due to symmetry, if we flip to the positive side, the two tails would be identical. So this is our original p-value from the definition, all the work. But just to find the value, we flip to the positive side. Okay, it's not that, oh, now we change the definition. No, we don't go back and change the definition. Otherwise, you're making a big mistake in your understanding. We are now coming to the step to get the actual value. That's why we flip. So now, instead of looking at the negative value, I look at the positive value. Use the same trick. 4, if it's not on the table, I'm sure not. Find the neighbors. Sometimes you get 2 neighbors, sometimes 1. Don't complain if you get only 1 neighbor, that's good enough for you. Here we have a value less than 4, another one greater than 4. Right? Our 4 is in between. So the p-value is between these two. For the p-value, I said I want to write less, but I'm writing for everything. P-value is between this and that. Can we compare with alpha? What alpha is given? Alpha is 0.01. So p-value is between these two. No matter where p-value falls, it's greater than 0.01. Because p-value is greater than alpha. So we cannot reject H naught. Critical region method. Critical region is a region for X bar. If X bar is too bad in supporting H naught, you reject H naught and you accept H1. What X bar would be bad in supporting H0 and good in supporting H1? If the sample is too small, right? So if your sample mean is less than a certain value, so if it's too small, you would support H1 and reject H0. So this is the correct look for your critical region. To find this X star alpha definition, for alpha definition for type 1 error, then you write probability of this. You copy your critical region when H naught is true, or when mu is 20. Instead of X bar, you show the T. So T, okay, don't want to write so much. T, want to show you how the other side would look after substitute. When everything is done, you get to this step. And this would be the last step before you pull it out of the probability. Alpha is this, right? This is the probability for T to be less than something. Back to the T, the PDF of this T. Remember this T can be negative, positive, symmetrical about 0. T is less than something with a very small probability. It has to be on the negative side. Okay. This, I've already warned you that 80% of students in the final exam will pick the wrong side. Because the T table gives you only positive, then you only use positive? No. It depends on what you really have in the equations. T is less than. Then where to find this negative? With the left tail probability of 0.01, I'm sure you need to look at the positive. The positive one has this 4.541 from the T table. So the negative side, due to symmetry, again, this negative value is here. Now you connect. This is the same as if you have something like this for your z, no matter t or z, to find the negative t or z value, you have to start with a positive. Now you make these two to be equal. Calculate, draw a conclusion that you have the critical region now. The critical region is that value is this. Use it to conclude the test. Our 4 packs has the average weight of this much. Right? This, it is less than 20, but is it that significant? Is it less than that? No, it's not. It's greater. So if the 4 packs gives you the average weight of less than this, then we say mu is less than 20. So this is the significance. That's the critical value for you to make decision. Our value is more than this cutoff. Same conclusion. You cannot reject H naught at the 2 examples are done. I'm going to just remind you of the 3rd method. So I've explained critical region p-value method in both situations. So we've covered both kinds of the one-sided test. The course this month does not cover one-sided confidence interval. That's why we've not used confidence interval in these 2 examples. So let's just just imagine. Okay, let me just imagine that the situation has changed. We still use the serial question, but now the claim is mu is 20 or not. So if it's not 20, I don't care if it's more or less. So it's just 2-sided test. I use the same random sample. So this is the only change. So just to introduce critical region method. A random sample. I'm not going to calculate anything. Just want to remind you of the idea. Use a confidence interval to conclude the test. Since the hypotheses have changed from the previous one-sided to the two-sided, our conclusion may not be the same because we are working on different hypotheses. So if you have time and you carry out all the calculations you found, oh, I don't have the same conclusion. It's all fine. Okay, don't panic. What is confidence interval? Back to handout 4. No, handout 7. Sorry. The idea of confidence interval. We know nothing about mu, right? Nobody should know anything about mu because it's from the population. But we have our sample, and we believe that this sample gives you some suggestion, some estimate of your population mean. The sample mean for our 4 packages have the average weight of this much. I put it on the number line. Can I say that since the sample mean is here, the population mean must be here? It can't be that strict. Instead, I give you an interval around the sample mean and say, since the sample mean is here, the population mean should not be far away. It should be around it. That's why I just round it into a two-sided interval. So mu falls inside. You can't say it has to fall inside. No, it falls inside with a certain probability. Right? That probability is defined as the confidence level. So mu falls inside with, what's the confidence level? With 1 minus alpha. Confidence. Alpha 0.01, so our confidence level is 99%. This is the idea. So let's find the confidence interval for mu in the same way as before. Confidence level, okay, this is 99%, is the probability that mu falls. This is the lower bound and the upper bound with two constants. Mu is here, know the direction. So all the nice work to reach the T, right? So I can't remember 3 or 4 steps to get to a T in the middle. Something here, something there. Once you have this T, you refer to your T table to find this and that to give you the probability of 99%. Back to this T. T is greater than something, less than something. It's a very high probability. That's why I have the main body covered. So find these two and then connect. Whenever you see I have long arrows, it's time to put them down. I will have two equations to find L and U. Once you have L and U, it's time to look at what value is claimed to be mu. If 20 falls inside, then you can't reject 20. If 20 falls outside, either or, either side, reject 20. It's as simple as that. Again, everything comes from the basic idea. So when you have a confidence interval question, you have enough time in the final exam. Okay, just draw this number line to make sure that you understand, okay, I need to use this. And in the end, you use the claimed mu value to conclude the test. Okay, this is a quick reminder of the third method, confidence interval. The handout has a table here. It says an alternative way of using critical region method. I don't suggest you to learn from this alternative way. I show it just because a lot of students learn critical region method from other people, right? From online, whatever, watch YouTube or something. They will use this alternative way. Now, it's not that we will not allow this alternative way. Just in case you are confused why we are using a different way as other people, this table compares that these two ways are essentially the same. But since you are in class right now, please use our way. Otherwise, you will say, oh, I have two ways for critical region. Well, let's just consider critical region as one way and we'll keep using the same. The other side of this handout is a summary of all methods. When you see this table, maybe it will not make much sense, but this table summarizes all the bell curves you saw me drawing for each example, each method. So it's a reminder. If you want to draw, just it's not a, oh, I just pick one. You just use the correct one. I hope that these all made sense. So everything starts from what pair of hypotheses you use. So if you do whatever actual practice questions, for example, the book exercises, if you have one of these given, when you use a particular method, double check. Now, because the book exercises will not give you all the figures, so make sure, for example, if you are doing this test, what you draw for the critical region method should look like this. Right? You should have a right tail. If you draw in your solutions a left tail, that would be wrong. So use this table in that way to double check. You have to understand the method in order to shade the correct side. So it's just a double checking. Now this handout is all done. Now we move to the next handout, which is our last handout for now. Two sample hypothesis test. We need two samples because we have two population means to test. To move from one sample test to two sample test, in terms of ideas, they are all the same. We use exact the same three methods. The definitions remain the same. The steps are all the same. The only thing is the work seems to be longer because we need to include two samples, right? We have, instead of 1 mu, we have two. That's the only difference. So you need to write a lot. Let's introduce the mu1, mu2. For example, x1, we define it as a random boy's height. We assume normal. Okay, I introduce mu1. So this is the average height of boys, sigma 1. x2 is a randomly picked girl's height. I introduce the two parameters. When you see this, they are not samples, they are populations. So the population for all the boys, they give you the normal distribution. This is the population mean, population variance. These two are probably girls' population. We only test on population means. So we test, for example, can I claim that on average, boys and girls have the same height? The sentence would be like this. Do they have the same height? Now, when we compare two things, they are both unknown. Nobody knows their actual population heights. I give you two options to compare. One is, what if I compare two things are the same or not? I can check if the ratio is 1. Or I can check if the difference is 0. Right? We know enough math to convert this equation into, can't we just leave as this? Right? The reason is, since they are both unknown, to have Two unknowns on the separate sides will not give you an actual number to test, right? We deal with numbers rather than two unknowns on the separate sides. That's why I'm forcing a number out. Then when I do the work or when I conclude, I will say, yeah, because one falls in, if zero falls in whatever region, so I have extra numbers to make arguments. That's why I'm changing this form to either or. Right? They are actually the same thing. Now let's see which one works better for us. Mu1, mu2 are both unknown. What gives you good estimate for the unknowns? Sample mean gives you good estimate for population mean. I write instead of population means into the matching of the sample means. So x1 bar is a group of boys I collect from this population. I get the group of boys height versus divided by a group of girls height. Right? This would be a good estimate for the ratio of the population means. I write in the same for the second case. Now let's have a look. X1, X2 are normal. So X1 bar, X2 bar will be normal, right? Handout 4. We have two normal variables. If they are in this way, linear function of normal variables would be normal, right? We will know that this would follow a normal distribution. However, this is not linear. This is a nonlinear function of normal variables. It's not normal, okay? This is not normal. Okay, this is not X, it's wrong. This is not normal, this is normal. That's why this is a better way to do our test. Okay, I made argument to say why it is a good idea to test the difference rather than the ratio. Okay, this is already a big step. Alternatively, okay, for example, I want to test the claim that on average, boys is taller than girls by 2 centimeters. So instead of whether they have the same height or one is taller than the other group by a certain value, so this does not have to be always zero. I can test on a different value. So it all depends on what the test is. This is a start of two sample tests. For the Handout 9, we have different cases. We have 4 cases. Today, probably we can cover the first case, which is the easiest. I write out all the information you need to know for the case 1. So if x1, x2, two variables, for example, girl's height, boy's height, the two variables are independent, right? Because you random pick the boys and girls, make sure they are not genetically connected, they are independent. And population variances are known. Okay, I copy the notations for the two normal distributions. If sigmas are known, we have two samples. This many boys are collected, and this many boys' average height. this many girls and their average height. Do we need S1, S2? No, we don't, because we have sigma 1, sigma 2. With this, the sample mean. This sample mean is, so this is the way to calculate any. The first boy's height plus the second boy's height plus, then divided by the total number of boys. This is a linear function of random of normal variables, so it's normal. Do the same for the average height of the girls and two girls. Right, so I have x1 bar, x2 bar are two normal variables. Because we are using the format mu1 minus mu2, so I do x1 bar minus x2 bar. Normal minus another normal is normal. What's the mean of this? The mean of this expression is mu1 minus mu2. My suspicion is you can't remember much from Handout 4. So mean of x1 bar minus x2 bar is this, then the variance plus, okay, plus, right? Why it's plus? Review, okay, Handout 4. We know sigma 1, sigma 2, we know n1, n2. This is the unknown, z. This is the normal thing that follows a normal distribution with this mean, that variance, standardize. Standardize this expression by subtracting its mean, right? And divide this by the standard deviation, so the square root of this variance. Now you see what I meant by you just need to write double the length. Right? Previously, we just have x bar minus mu sigma square over n1. Now we just double because you need to use two, all right, two sample tests. It's not that three sample tests you write even more. No, we have a different method if you have more than two. This is the setup for your case 1. Now let's do the first example. The first example is quite long. Okay, let's see how much we can cover today and the rest for next time. The first paragraph, a builder. So there are two types of paints, brand 1, brand 2. Brand 1 is the traditional one he's been using. Brand 2 is the new one. That claims to reduce the drying time. But because it has a good property, it has extra cost. The builder would switch to the new one, the expensive one, if the drying time is reduced by more than 30 minutes. So with this much saved time, he can earn extra by doing some other painting work. So this is the background of the test. We are testing not the difference in cost, but the difference in the drying time. We introduce X1 to be the drying time of brand 1. Okay, let's start. X1 is the drying time of what? Of using brand 1 if you paint once, right? If you paint a random thing once in minutes, of using brand 1. X2 is the drying time you paint with brand 2. Do you think X1, X2 are independent? Of course they are, right? You don't mix them. X1, X2 are independent. We started case 2 with the same condition. They are independent. But why is it useful, right? I don't remember where we used it. We used here variance of these two. This is a linear function of two variables. If we don't have the assumption of independence, the variance of this linear function would have a covariance term. We don't have the covariance term here because x1, x2 are independent. So their covariance is 0. So that makes it important for you whenever you are dealing with different things, with two variables now, you need to see whether it makes sense to claim that x1, x2 are independent. Here, yes, the two paints are independent of each other. And the second paragraph, a lot, so just trust me what I write. I'll write all the numbers here. It tells you that x1, x2 are normal. So let's introduce the notations that we are going to use in our work. The question tells you the standard deviation of the two paints. The drying time of both brands follow normal distribution with standard deviation of 10 minutes. This 10 minutes appear in the sentence that the drying time of both follows normal distribution with standard deviation. So the standard deviation is for these normal distributions. That's why it's not sample standard deviation, it's population standard deviation. So I use the 10 for sigma 1 and sigma 2. Let's get used to this. The combined expression of the two sample means, oh, not common, minus the test is whether using the brand tool, the more expensive one would save more than 30 minutes in terms of drying time. So 30 minutes is the decision. Mu1 is the average drying time of the cheaper brand. It takes longer to dry. So you expect mu1 to be more than mu2. That's why, because I prefer to work with positive numbers. So I use the larger one minus the smaller one, whether the difference is 30 minutes or more than 30 minutes. Right? This is the question the builder has, whether the time saved in the drying, is greater than 30. So this is hypothesis test all done. Okay, this is all the necessary setup. We decide T or V statistic is T. No, not Z, because these two are given. So it fits perfectly to the case one. I set up and then I'll bring these notes to the next lecture and we'll start from there. But let me copy the two samples. The builder used both brands 10 times. Brand 1 dries on average this many, right? 2 hours is their average drying time. 85 minutes is for the second brand. Okay, this is a complete setup. We will continue next time. If you have questions, please ask in the space. I also do office hours in the afternoon remotely. I'll send message on the team space.